Hello everyone. My name is Jelte Hoekstra. I'm from Amsterdam. And today I'm going to tell you about a Kaggle I participated in last Christmas. This is a different Kaggle than the usual Kaggle because it's actually an optimization problem, which involves some data. So, a little bit about myself. I studied computer science and artificial intelligence in the Netherlands. After that, I did a few internships, and then I became a data scientist at GoData Driven, a consultancy company based in Amsterdam in data science and engineering. We're hiring. Finally, I participated with my colleague Vincent Warmerdam, who's speaking next door at this moment. So, the problem. I just told you it's an optimization problem, and the thing is that Santa has to deliver presents, but he lost the list of which toy should go in which bag. So now he's trying to find out how to fill 1,000 bags with toys. And for this, he needs to maximize weight. He wants to pack as much weight as possible, but he can't pack too much weight in one bag because then it will tear at 50 kilograms. So for this Kaggle, you have 120 submissions, which is important, as will turn out. So far, so good. But one thing is different than usual, and that's the toy weights are unknown, but fixed. So if the toy weights are unknown, what do we have? We have these distributions. So for example, I have a horse, and I know that on average, this horse weighs about 6 kilograms. So some of these look quite normal, but others don't, of course, if you look at Cole or the gloves ones, for example. So the toys that you are going to use, they were sampled from these distributions. So for example, you get 6,000 horses, and each of these were sampled from these distributions. But you don't know the weight of a specific horse, so horse 24. Yeah, so this is basically what it looks like, what you got. So if you have any background in optimization, I think you will probably wonder, is this a knapsack? For those who don't know the knapsack problem, it's an NP-hard optimization problem where you have to put stuff in bags. So of course that sounds quite similar. You know the weights and you know the value of items, and you don't have to pack all of them. So in this case, we have to pack multiple bags, so that's why it's a multiple knapsack, and we can write down an optimization problem with all the constraints and all that. But still one thing is missing, and that's the weights, because we don't know them. So the first thing we thought is, can we estimate these weights just by using the PDFs of the toys? So for example, you could take a horse toy and you could say, well, I expect this horse to be 6 kilograms on average, so I'll just use this in my optimization problem. For solving this, we used Google OR tools. So it's a unified interface to a set of solvers. So it has Boolean satisfiability, it has traveling salesman problems, and also ILPs, so the one we used here. You can construct your problem in Python, it's quite nice. So you say, okay, I have this objective, I have these constraints, and I need a solver, and go. It's really as easy as this, so you can add them with a loop. And it's really, well, once you've written down the math of the optimization problem, it's quite easy. So this is what we did. But it turned out that it didn't really work. And it didn't really work because a lot of these bags will tear. If you look, for example, at these gloves, you will see that they come in two variants, basically. So you have a light one, which is about 1 kilograms, and you have a heavier one, which is 3 to 4 kilograms. Now, if I take the expected value of this gloves toy, I will get somewhere in the middle. So for half these gloves, I will sort of underrate the weight that they have. So when I start packing, then often these bags with gloves will tear. And that's why this doesn't work in practice. Now, there are multiple things you can do to resolve this. The first would be to actually relax your problem. So if this is your optimization target, you can say, okay, I mean, if this is your constraint that says you need 50 kilograms max in a bag, you could say, well, let's not try to pack 50, but let's try to pack a little bit less to see if this will cause fewer bags to tear. And this is the case, and you can play around with this. But it's still a bit wacky, and it doesn't really work out in the end, because it's still a mismatch between the weights that you give in and the actual weights. Now, there's also a different solution. And this different solution involves looking at entire bags instead of specific toys. So the decision that my optimizer will make is now, will I use this specific bag, which is, for example, 2 horses and a book? Or will I, instead of saying, should this specific horse go in this bag? So you make it a different problem. So for this, we would need the bag weights, which we don't have, of course. But we do know, we do have the probability distributions for the specific toys. So what Vincent and I did, we said, okay, of all the combinations of toys you can make, let's try all the combinations of toys up to 11 toys. I mean, at some point you can't do this anymore because there are too many combinations. And let's just start sampling from the toys and see what comes out in terms of the weight of this bag. So on the left here you see the weight distributions, for example, for a bag which contains 1 bike and 3 trains. And on the right you see the utility, so that's the actual score that I expect to gain from this bag, which is different because, of course, if it's heavier than 50 kilograms, it will tear. So you see that we clip there, and then there's suddenly a huge spike at 0. So this we did for all possible bags up till the 11th power. And then you see this. So if you would map out of all these possible bags the expected value, the expected utility, so what you expect to gain from it, versus the fail probability, like how often did this bag actually tear in my sampling, in my simulation, you'll see that there are different kind of bags. So some of these are low risk and high value. So these are the ones you see in the left corner. So those are the bags that are sort of always around the same weight. Then there are some bags that are actually have a higher fail probability. So those are the bags that are closer to 50, but they'll fail more often. And now the question is, which of these types of bags should you use in your optimization? So we tried around a bit with this. So here the red line is expected, as in the expected value by computing with the ILP. And the blue dots are the actual values that we got when we would simulate this with different kind of gift permutations. So what you see is at the horizontal axis, if we take more risk and we increase the max fail probability that we allow in our bags, we see that at some point the results start to level off and you don't get any more score. But that's on average, of course, because there we would simulate over 1,000 shuffles maybe. But what you might want to do, so for example here we said, okay, we looked at where are the actual highest results on average. So that's maybe around 0.4 fail probability. Then we pick this solution. And of course you have 120 submissions, so you can actually permute the, like, you know, if you, instead of picking horse 6 for this bag, I can also pick horse 7, and it will make a difference in the score that I get back. So I can just try a lot of times. So one person on the forums actually tried this in a simulation, So the blue distribution that you see here are the sort of the resulting scores that he got back. And the green distribution is if he would submit 60 times the same solution structure, the best scores that he would get. And you'll see that actually the best score in 60 tries is of course better than the average score. But he also concluded that this solution isn't really very viable to get a high score. So then we thought, would it be possible to use some of our submissions to learn something about the test set? And this is actually where the competition got interesting. So for this we used PyMC. It's a probabilistic programming framework for Bayesian modeling. So you can set up graphical models and compute all kinds of posterior distributions. So for example, you can ask questions like, if I know that I have a 70% chance of getting the flu, what are now the probabilities, or what does the distribution look like for me to get muscle pain or congestion? Other questions you can ask also are the other way around. So you can say, okay, if I actually notice that I have muscle pain as an observation, what is now the probability distribution for getting flu? And we could also do this for this problem, where we say, okay, I have a few toys, for example, 2 horses and a ball, and now I'm going to combine those and put them in one submission. So we would submit only a few bags with only a few items, and we'd see, okay, what's the score we get back? And we'd do that multiple times with sort of overlapping. For example, horse 2 goes in multiple submissions, else you can learn, of course. So if you want to do this in PyMC, it's actually quite easy. So at the top you see we define these weights, and then we say, okay, these random variables, what sort of distribution do they have? So here we say normals, but they would actually be the specific toy distribution. But this was a tryout to see if this has any value at all, or if it's possible. And then you say, okay, I had a few observations. So here we say we had 3 different submissions of combinations. And then we start tracing or sampling. And you can actually see the sort of bar at the bottom because it's sampling, so you know when you will be done, because it's a set sample size. So what do we get back? On the left here we see the posterior distribution. So what the sampler came up with. You see multiple lines because these were the different, we did it in parallel on different cores. And it's interesting to see that for the 2 of the weights or 2 of the toys, all the different threads came to the same conclusion, so the bottom ones on the left. But for the other ones, they actually found multiple solutions, and that's because if you look at the system of equations, there are actually multiple solutions. So, for example, one solution is that mu2 would be 4, mu1 would be a weight of 2, but you can also turn this around, or you can say one is 5 and the other weighs 1, and actually multiple solutions are found. On the right, we see the trace plot, so that's sort of how the sampler progressed. And we find that it actually converges at some point. So then we try to wrap this up a little bit. So we said, okay, now we have multiple toys and we have fewer equations, basically. Can we still do it? Can we, with larger bags of toys, can we still learn? And basically the answer is that it's complicated. We see that the sampler didn't really converge, so there wasn't much learning going on there. And that's basically where we quit our participation in the competition. However, when you look at the leaderboard, and this is the distribution of the public leaderboard over time. So the big spike is a public submission that a lot of people will also submit, of course. We will see that at the front, a few people just keep steadily progressing, and they kept getting better and better and better. So you start wondering, what have they been doing? So I already said that I can submit the same solution multiple times, and I can permute the IDs of the gifts. So instead of horse 7, use horse 6. And this will probably gain me a little bit. Now you could also do this in a sort of binary search way, where you say, okay, I split my solution, and now I submit half of it, so 500 bags. And then I say, okay, is this score that I get back, is it below or above average? And if it's above average, I want to keep it. But if it's below average, then I want to permute it a bit. And this way, you actually get a lot more results than just permuting everything all the time. A second approach that I read on the forums is called coal mining. So basically, one of the toys has this peculiar distribution where it's either very either has a very low weight, or it actually has a really high weight, but really as high as almost 50. So this would be a bag in itself. So then one guy, early on, realized that if he would mine enough of these coals and he know their exact weights, he could actually assemble a good bags one at a time. So we started doing that, but of course it's a bit slow, and you only have 120 submissions. And then he came up with this. And this is actually quite a clever trick that a lot of people copied later on, because he shared it meanwhile. Basically how it works is I have a few bags, and now I'm wondering, is one of these overweight? Is it going to bust? So what I'm going to do is I'm going to submit it, and I'll get back a score. And you see, if you look at the top table, that one of these bags actually is overweight. So I can immediately see, okay, it's overweight. Now I will have a few items, like lightweight items, for example, gloves, that I already know the specific weight of. And I will add to each of these bags one of these small items. And then I will say, because maybe I should mention that what you're actually trying to find out, of course you can see it, the score is 95, so one of them bust, but you don't know which one it is. So that's the thing you're trying to find out now. So you add these small lightweight items, and then you say, okay, what's my score now? And then you can just look at which of the linear combinations will actually, of course you have to make sure that these extra weight items, these small items, all have a different weight. And then you can see, okay, I know the difference between the score before and after. I know which of these two extra items actually moved on. And now I can see that, okay, apparently bag 3 was the bust one. And now I'm doing it only with 3 bags, but if you have multiple of these lightweight items, you can really scale it up. So some people did this with 20 different bags at a time. And if you only have to fill 1,000 and you have 120 submissions, you can actually get quite far. Now, of course, you can do all this effort and solve ILPs and try to really learn from your extra submissions. Or you can actually take a look at the random number generators that produce these items and actually try to enumerate those. And one guy did this, and at the end it turned out that he had actually cracked the seed, so he could completely show the entire item weights. So that's also a solution. Okay, thank you.
Thank you very much. Anybody questions?
Thank you for the presentation. I'm wondering if there is some kind of real problem where you can use this solution to this learning optimization problem.
Yeah, well, I think in that case you're basically looking for real-life multiple knapsacks, of which there are definitely examples. I don't have one with me at the moment, but if you type this in, in Google, you will find a few, I think. Yeah.
Okay, I think. Thank you very much. I think we